Good morning, good evening. Welcome to the next Gen 4 International Forum webinar presentation. Today's presentation on corrosion and cracking of supercritical water-cooled reactor materials will be presented by Professor Lefou Zhang. Doing the introduction today is Dr. Patricia Pavier. Dr. Pavier is the chair of the Gen 4 International Forum Education and Training Working Group. She's the National Technical Director of the Molten Salt Reactor Program for the DOE Office of Nuclear Energy. Patricia.
Good morning, good evening. Thank you very much, Bertha. It's a pleasure to have Dr. Lefou Zhang with us today. He's a professor at the School of Nuclear Science and Engineering of Shanghai Jiaotong University, and he received his bachelor, master, and PhD degrees in material science from Huansong University of Science and Technology in China. His research focuses on materials and water chemistry for light water reactors. He established a joint research laboratory for corrosion of nuclear power materials with Shanghai Nuclear Engineering Research and Design Institute in 2008. Under his 15 years of leadership, 80 high temperature and pressure water circulating loops have been built for general corrosion, stress corrosion cracking, fretting wear, fuel cladding tube performance, and water chemistry tests. And among them, 15 systems are for supercritical fluid reactors. He is the Chinese representative in Materials and Chemistry Project Management Board and the Chinese substitute representative in System Steering Committee of Supercritical Water-Cooled Reactor System in GIF. So without any delay, Professor Zhang, thank you very much for volunteering to give this webinar, and I give you the floor. Thank you.
Okay, thank you, Patricia. Thank you. So good morning, good afternoon, and good evening, friends from all over the world. It's my great pleasure to make this talk and share some of our experience on the corrosion of supercritical water-cooled reactor materials. For better understanding of what I will talk, we need firstly to review briefly the technical background of SCWR. So in the year 2001, Generation 4 International Forum was created as a cooperative international endeavor seeking to develop the research necessary to test the feasibility and performance of the fourth generation nuclear systems and to make them available for industrial deployment by the year 2030. It's very near now. 6 conceptual reactors were selected by GIF. They are the gas-cooled reactors, lead-cooled fast breeder reactors, molten salt reactors, supercritical water-cooled reactors, sodium-cooled fast breeder reactors, and very high temperature reactors, gas-cooled. So among them, SCWR is proposed as a high-capacity electric power generation reactor for future nuclear power plant. The outlet steam temperature is expected to go up to about 510 degrees centigrade for a pressure vessel type reactor and up to 650 degrees for CANDU type reactor. And the expected thermal efficiency is over 46%, which compares with the LWRs is nearly 10% higher and 10 times higher fuel efficiency as compared to a PWR reactor. Furthermore, the SCWR design is identified with a simplified design with industrial material curbing from supercritical fossil-fired plants. It eliminated the headache systems of a PWR, such as steam generator, pressurizer, main pump, and making the cost lower for future constructions. The SCWR is much likely a BWR, but water does not boil in the core. It directly turns into supercritical water or steam. So, however, scientists are facing great challenges in selection of the fuel cladding material for SCWR. Presently, we have two types of SCWR conceptual design. Namely, they are pressure vessel design, and here this is a pressure vessel design, and the pressure tube design, which designed by Candu. We did not include this in our presentation because they have much higher outlet temperature, which is about 650 degrees centigrade, which I consider very, very difficult in materials and chemistry. So in this pressure vessel type reactor, with the water goes to the core is usually considered to be 280 degrees C, and which is similar to a PWR or BWR, but the outlet temperature is much higher, usually about 500 degrees C. To keep the water in supercritical state, the pressure is kept not less than 25 megapar. This is the Euro pressure. For pressure vessel type SCWR with core outlet coolant temperature of about 510 degrees centigrade, the fuel cladding hot spot or peak temperature will go up to over 600 degrees centigrade, and the calculated hotspot may go up to about 650 degrees centigrade. At this temperature, none of the zirconium alloys currently used in the LWRs can survive a week before turning into dust. This is with very high oxidation rate of this material. Scientists has proposed several austenitic stainless steels and nickel-based alloys to be the candidate fuel cladding material for SCWR. However, the screening test also show many concerns in general corrosion, creep, and stretch corrosion cracking after nearly 20 years of study. And the current knowledge about materials and chemistry is still weak to support the construction of a demo supercritical water-cooled reactor. Our current choice should either to reduce the outlet temperature in the core, or investing on R&D of novel materials, which is very expensive in the future. So as most of you have known that supercritical point of water is at 374 degrees centigrade and 22.1 megapascal pressure. The phase changes at the critical point and cause significant changes in physical properties such as heat capacity, density, and thermal conductivity, dielectric capacity, and also chemical properties such as solubility to organic materials, gases, and ionic compounds. The bad thing is that the self-decomposition of supercritical water leaves relatively not low dissolved oxygen concentration in the water, which turns the supercritical water into a very oxidizing gases. And this is why many industrial applications to use supercritical water to oxidize very dangerous materials like the poisonous materials. When we what? Sorry. So in a typical pressure vessel type supercritical water reactor design, the water usually goes through 2 or 3 passes through the core and changes from supercritical, subcritical to supercritical state. The multi-pass of water through the core is needed to balance the neutron moderation due to the dramatic change in water density, so that the core power density will be more uniform. The thermodynamics and neutron physics are not of our great interest. We now focus on the materials and chemistry. The performance of material in subcritical and supercritical water show significant differences. So in subcritical region, let's say when the temperature below 374 degrees centigrade, the polarity keeps water in liquid states, and electrochemistry controls this solution and corrosion of metallic materials, and electrical reaction and controlled general corrosion, stress corrosion cracking are the major concerns in this temperature region. We've collected abundant experiences in this regard in PWRs and BWRs. And at critical point, at critical region, let's usually say between 375 and 390 degrees centigrade, the polarity of water molecule drops significantly, and the solubility of ionic species decreases accordingly, which makes the dissolved ionic metallic corrosion products deposit on the component surfaces or turn into metallic oxide particles. This is the major cause of deposition of crud on the fuel cladding in this, and this is also the major concern in this region. In supercritical region, the high temperature provide reaction activation energy, and dissolved oxygen provides reactant for the oxidization of metallic materials. And meanwhile, as creep temperature of the austenitic stainless steel and nickel-based alloy is usually at about 450 degrees centigrade, and in supercritical water, creep-induced cracking will be unavoidable and will be one of the major concerns. So to face the high flux of neutron irradiation, high pressure of the water, structural materials for key components for water-cooled reactor are usually all metallic materials, iron-based alloy with nickel, chromium, molybdenum, or zirconium, or nickel-based or cobalt-based material are the major materials to form these materials. However, these elements, these materials are naturally in oxide, in ionic states, and they will turn back to their stable state if there's no protection method in our engineering components. Formation and keeping the integrity of a protective oxide on the metallic components are the only way to make them survive in the reactor for a very long expected time, for example, 60 years of operation in the water-cooled reactor. The oxide film on the zirconium alloy is usually zirconia, ZrO2, which the zirconium element is very insoluble in neutral water. However, zirconia is oxygen vacancy conductive at high temperatures and is unprotective to the diffusion of oxygen, which leads zirconium to be oxidized very quickly at temperatures, say at about 500 degrees centigrade. If at temperature about 650 degrees centigrade, the zirconium alloy will soon turn to dust. So for this material can't be used in our supercritical water-cooled reactors. And for the oxide film on austenitic stainless steel or nickel-based alloy or cobalt-based alloy is usually a chromium-rich oxide, such as chrome-rich iron, nickel, or cobalt spinel, which plays the major role in protecting the inward diffusion of oxygen and the outward diffusion of atoms in the material matrix, especially iron atoms. The surface oxide film on the surface of austenitic stainless steel or nickel-based alloy is usually a 2 or 3 layered oxide. In supercritical water, the oxide film usually forms a 2-layered structure. The inner oxide layer is formed by the oxidation of metric material in the surface, and the outer layer is formed by deposition of ionic corrosion products. And this is usually uses chromium, so Cr2O3 as the protective oxide. In supercritical water or high temperature steam, oxide films usually forms a 3-layered structure. The outer layer is formed by fast diffusion of iron. The middle layer is a chromium-rich spinel, and the inner layer is formed by diffusion of oxygen into the matrix and react with the matrix metal atoms. So usually we say this is the internal oxidation layer. So after a long time of experimental tests and engineering applications, we've now known that the protective oxides are mostly chromium, aluminum, silica, zirconia, or chromium-rich spinel, or chrome aluminum-rich oxide, so that they are protective. The problems that damage integrity of the oxide film is usually the evaporation of chromium, aluminum, and silicon in high temperature steam or water. We need to either alloy the material with high concentration of chrome, aluminum, or silicon, or to provide their supply to balance the loss of the element that so that the protectiveness of the oxide film will be maintained. So the kinetics of chromium Cr evaporation or depletion show that the temperature, oxidant, and the steam velocity are the major factors that bring it away. Diffusion of chrome is the only way to supply to the surface oxide to maintain the protectiveness of the surface oxide film. So chromium concentration, dislocation density, green boundary density are the major factors to supply chrome atoms to the surface oxide to maintain the integrity of the oxide film, as these are calculated in the diffusion equations in here listed in here. If you want to learn more, so please refer to this reference. And here we can say that in the diffusion coefficient of the chrome, we can say that dislocation density and grain size are the major factors to affect the diffusion of chrome. And if we check the flow of the water, we can see the laminar flow and turbulence flow acts similarly on the mass transfer of chrome, but with different coefficient. So the flow of the water deplete the chrome from the surface oxide. So as compared to the fire tube of the fossil-fired plant, the fuel cladding has a thickness of about 0.4 to 0.5 millimeter, which is very thin in compared to the fossil fire tubes. It is too thin to resist the corrosion by supercritical water for total exposure in the core for 5 full power years for most of the currently material. We have to select materials with very high concentration of chrome and addition of aluminum to reduce the corrosion rate of the material based on our current study, test, and experiences. Now, after 2 decades of research, the short-listed structural materials for SCWR are short-listed, and presently alloy 800H and austenitic stainless 310S are considered to be the best selection for fuel cladding application in the core. And P91 and 92 is considered to be a good choice to make pressure vessel and primary piping. At present, the major concern of the supercritical water-cooled reactor materials are general corrosion and stress corrosion cracking. Due to the lack of experience and knowledge, we had bad data in our previous test, and now we can turn to our concerns and focuses on the material for SCWR. The major research work of materials and chemistry for SCWR focuses on screening tests to understand the corrosion and the cracking mechanisms of commercial materials for the development of novel materials. Our destination, our aim is to develop new materials. But before that, we have to understand many factors. And firstly, the chemical composition, chrome, aluminum, and silicon effect on general corrosion and stress corrosion cracking. And we have to understand the grain size effect and how to apply cold work and heat treatment to obtain fine grain size to achieve lower corrosion rate while to maintain the creep resistance. So, use cold work to introduce a little bit higher dislocation density to accelerate the diffusion of chrome and to control corrosion rate, and to use of precipitation hardening to control the effect of creep on crack initiation and crack growth. So at present, although we have so many data, we still have are very lack in the corrosion and cracking of the material. And presently, radiation hardening and enrichment is not the major work of our big concern. So let's look at the commercial alloys we have considered for SCWR fuel cladding. In the early years of research, we tested the ferritic magnesitic steel, such as P91, P92, P122, which contains about 9 to 12% of chromium. These are usually selected for construction of reactor vessel and piping. Their performance has been studied intensively for the application in supercritical fossil-fired plants. We need to borrow the data and experiences from fossil-fired plants, as their operation conditions are nearly the same in the SCWR. However, the corrosion rate, general corrosion rate of ferritic magnesitic steel in supercritical water are generally too high for the application as a fuel cladding. Let's see this figure, and the thick oxide film on the surface of the FM steel, which is at about 600 degrees centigrade for 1,500 hours. And next, for the austenitic stainless steel, is considered most promising materials for fuel cladding of SCWR. 304, 316, and 310S steels have been studied very intensively. Green boundary diffusion of chrome is one of the most important ways to supply chrome CR element to the surface oxide to maintain the integrity of the oxide above the green boundary, so that this here is protected when we see that at the initial stage of exposure of stainless steel. And the diffusion rate of chromium in the green interior is much lower. It's usually 2 orders of magnitude lower than the green boundary. So the diffusion of chrome is not enough to supply enough chrome to the surface oxide. So in the oxide film, after some times of exposure, chromium will be depleted, and so the iron will diffuse out and oxygen diffuse in, so that we can say at the initial stage of exposure in this material, we will see island-like oxides on these materials. This is because of the low chromium concentration, or there's a lack of chromium diffusion mechanisms to maintain the integrity of the oxide film. So for better performance in general corrosion rate, we usually need to increase the chromium concentration up to about 25, and this will be the austenitic stainless steel 310S. this material. The major concern of austenitic stainless steel in a PWR plant is the stress chlorine cracking, which is significantly affected by cold deformation, dissolved oxygen, chloride ions, and other negative corrosive ions, and also sensitization of the material. In a supercritical water-cooled reactor system, the operation temperature goes up to about 600 degrees centigrade, 650 degrees centigrade on the cladding material. It is well above its sensitization temperature. Usually we say 450 degrees centigrade for austenitic stainless steel. So sensitization will be unavoidable in a high concentration, carbon concentration austenitic stainless steel. So usually for high strength, we need to add a higher concentration of carbon into the steel. But in this, this will assist the sensitization of the material and makes the stress chlorine cracking. We have to reduce carbon concentration to below 0.03% to reduce the susceptibility to sensitization and intergranular corrosion. For austenitic stainless steel 310S, we've ever did a lot of study on general corrosion and stress chlorine cracking. And the general corrosion rate of 310S is very low. And in the following slides, we will use it as a standard comparison of material. However, the cracking of 310S is also very susceptible to the supercritical water, especially at temperatures above 450 degrees centigrade. The cracking is usually along green boundaries and is the major form of austenitic stainless steel in supercritical water environment. The major cause to this phenomenon are usually sensitization and creep. The cracking are mostly intergranular. Let's say these figures, and we can also see voids ahead of the crack tip, and this shows the effect of creep plays very important role in this in the growth rate of the material, crack growth rate of the material. And austenitics, this alloy 800H is considered to be a super austenitic stainless steel, or is sometimes considered as a nickel-based alloy. So this material usually has high strength, especially high creep strength, and is shortlisted as the major candidate material for fuel cladding of a supercritical water-cooled reactor. But we put great effort in clarifying the controlling factors in general corrosion and stress chlorine cracking of this material. Our current work showed that cold work induced high density dislocations and green boundaries is a major factor to control its corrosion rate in supercritical water. Here, we can say that we used cold rolling to introduce high concentration, high density of dislocation, and with the increase of dislocation density, we'll have lower corrosion rate in the material. And here we also say that the surface finish of the material will also plays very important role in the general corrosion of the material, because the coarse grinding with coarse paper, emery paper, will introduce much higher density of dislocation at the top surface, and this will accelerate the diffusion of chrome and to maintain the integrity of the oxide film, so that the corrosion rate of the material will be much reduced. And this will lead to a process to control surface finish in fabrication of field cladding tube. A surface layer with either high density of dislocations or green boundaries is of great importance to reduce its corrosion rate. And the application of short pinning in fossil-fired plant is probably suitable also for fabricating the cladding tube of a SCWR. So this figure shows the importance of surface polishing when we do the exposure test. If we polish the material with very fine emery paper to make a very deformation-free surface on the top material, then the corrosion rate of this material will be very high, because of the less of mechanism to accelerate the diffusion of chrome. If we say there is a very high density of dislocation density, then we can get very thin oxide film with high concentration of chrome, and a little bit for aluminum, which is allowed in this material, and silicon so that the general corrosion rate of this material will be much reduced by the diffusion of the diffusion in the dislocations. So the green size is also a major factor to affect the chromium diffusion. So a very thin layer of surface chromium oxide will reduce the diffusion of oxygen to a very low level and protects the material from being oxidized in supercritical water. The thin layer of chromium requires to be maintained by diffusion of chrome during long term of operation, either assisted by very fine green size or high density of dislocations on the surface. Now we also studied the effect of creep on cracking of alloy 800H by using compact tension specimens. We say the CT specimens at temperatures between 450 and 550 degrees centigrade with 20% cold worked and higher. Also, by using a DCPD method to measure the crack growth rate, the crack growth rate of the alloy 800H in supercritical water and argon gas were obtained on the same CT specimen after switching the environment from supercritical water to high purity argon gas, so that we can, at the same time, with the same specimen, we have the effect of corrosion and creep on crack growth rate. So from this figure, we can say that at temperatures above 450 degrees centigrade, the crack growth rate shows that the major factor to control cracking of the alloy 800 is corrosion at temperatures above 500 degrees centigrade and below. It's the cracking, the creep plays very important role, and the separation for the controlling factors to cracking is important for future development of novel materials. And for these materials, sensitization is also a big problem because the carbon concentration is also not low. We also studied alloy 690, which has nearly no strengthening method except the alloying strengthening. In the supercritical water, we can say that the stress corrosion cracking of the material is nearly the same as a crack growth rate induced by creep, because there's a very weak strengthening method in this material as compared to alloy 800H, which is usually strengthened by carbide, precipitation of carbide. And so for the irradiation effects, should be considered in our future development of the material, but currently is the secondary important issue for SCWR materials. Radiation accelerated nickel depletion and nickel enrichment at green boundaries will induce higher corrosion rate and stress corrosion cracking of the material. And here we can say that these are the percentage of increased by the diffusion of chromium, iron, and nickel at the green boundaries. So slow strain rate test by Gary Wall's group showed that the test show increased SCC susceptibility of stainless steel and nickel-based alloys in SCWR after irradiation. And we can say that after irradiation, we can say that there is a higher percentage of intergranular corrosion can be found on the surface of the test coupons. However, facing the high corrosion rate of the materials, irradiation damage is at higher temperatures, especially at about 450 degrees centigrade, not the biggest concern in our current difficulties. We need to consider this problem in our future R&D of novel materials. So if we make a brief comparison of the candidate materials, so for FM ferritic martensitic steels, they have high strength but lower corrosion rate and good resistance to SCC, but it has too high general corrosion rate to be used as fuel cladding. It is majorly used for primary piping and pressure vessel. Stainless steel, especially 310S, has very good general corrosion resistance, but the SCC problem is still exists. And nickel-based alloy, it has too high nickel, but it has a lower general corrosion rate and good resistance to stress corrosion cracking. But for the future development of fuel cladding material, it is a secondary selection. So now let's turn to the novel materials. For R&D for novel materials, now we are facing very big difficulties. But we are still insisting on to find new chemical compositions and with excellent corrosion resistance and higher strength and with better stress corrosion cracking performance, combining the irradiation and other nuclear performances. So if we see the trees of the material based on alloy 304 and 316L, we better to add more chrome to reduce the general corrosion rate, and also add aluminum to further reduce the general corrosion rate, so that we can have better corrosion resistance. And for good strength, we need to better consider with ODS oxide dispersion strengthening method, so that we can have a yield stress up to 300 megapar at about 550 degrees centigrade to meet our need to make the fuel cladding further thinner, for example, to below 0.04 millimeter. But ODS may also introduce oxygen defects. This is a big issue at the current problem to make a good material. And for the pinning for green boundary, and it is very important to development creep-resistant material. So the current information tells us that cold work induced dislocation will increase the creep and stress current cracking susceptibility, but we need this to accelerate to reduce the general corrosion rate, but we need to have some strengthening method. For example, GD carbides at green boundary and precipitation in the green at along green boundary to pin the green boundary, so that to lower the creep rate and creep induced cracking of the material. So for the we considered the high concentration chrome, aluminum forming austenitic stainless steels, which we say these AFA alloys, and they were studied with chromium up to from 14% up to 25% of chromium, and aluminum up to 4.5%. A further addition of aluminum above 4.5 is impossible, because the material will be very brittle. And the addition of aluminum element to the material will change the microstructure of the material. It will precipitate. The precipitate will change in fraction volume. Here we can see the precipitation in fraction volume, morphology, and tabs. And there will be a precipitation of sigma phase and B2 nickel aluminum intermetallic compound phase, and spheroidize the Love's phase, and precipitation of ferrite is delta ferrite. When we add to 3.5% of aluminum and above, this will be a big problem. And the addition of aluminum improves the corrosion, general corrosion resistance of material significantly. And here this shows, this figure shows the importance of the aluminum on reducing the general corrosion rate of the material. And here, from these figures, we can say the addition of aluminum will make the surface oxide film more thinner and protective on the top of the material. This result shows that that aluminum scale is uniform on the FCC phase side. Is uniform. Here we can see that the distribution of the aluminum will be very uniform, but on the BCC side, this is not that uniform, especially when there's a precipitation of delta ferrite. The result will be not bad, not good. Okay. And the addition of aluminum also changes the cracking performance of the material. And the addition of about 3.5 aluminum, when we test this material with constant load of 0.9 yield strength, 0.9 times yield strength, then we will say that with increase of time, it has longer, higher strain. So addition of aluminum has benefit on the high temperature stress and creep cracking. The oxide, the alumina oxide in the crack tip hinders the corrosion, and meanwhile the precipitates impairs the crack propagation. So we have lower crack growth rate in these materials. And we also studied the effect of a silicon element on improving the general corrosion resistance. If we add silicon to AFA alloys, the silicon will work with chrome and aluminum to form a very stable surface oxide, so that with the increase of silicon, then we will have much lower corrosion rate. The alloying the material with 1.5% of silicon can reduce the general corrosion rate of the material about 10 times lower than 310S stainless steel. This is the 310S. This result shows here we can see that the the formation of silica can be found about the matrix material along with chromium and alumina, improving the corrosion resistance. And so the synergistic effect of chromium, aluminum, and silicon on general corrosion resistance is of great interest in our future study. Oxide strengthening method is one of the major method to strengthen material for high temperature applications. We've tried to add nanosize yttrium Y203 to the refined green size for austenitic stainless steel and ferritic martensitic steels, so that they may have much higher strength. And so here we can say that the dispersed oxide in the material can form in the nanoparticles, and this can improve the high temperature stress while keeping its oxidation resistance. And here, this figure shows that if we alloy the material with ODS very carefully, and also with higher concentration of chromium and aluminum, then we can have very good general corrosion rate in the material. Here, these are the macrostructures. We see the dispersion for yttrium, and here we can see the very low general corrosion rate of these materials. So now let's make a general conclusions of my talk. The SCWR concept is facing great challenges in adding materials. No commercial materials are available at present, and the R&D of novel materials facing a great gap in general corrosion and cracking performance, especially great gap in this. So we need more data. The ideas for R&D of supercritical water-cooled reactor fuel cladding materials is recommended to be with a high concentration of chrome, say at least about 20% of chrome, moderate aluminum, because too high aluminum will make the material too brittle, and some, for example, about 1 to 1.5% of silicon. This will further reduce the general corrosion rate of the material. ODS, oxide dispersion strengthening, can be considered to strengthen the grain boundary and to reduce the creep rate, while to maintain the general corrosion rate of the material. And bulk or surface hardening by cold working is necessary to reduce the general corrosion rate of austenitic stainless steel, and maybe in the future short pinning will have to be applied in the process of fabricating fuel cladding tube for the supercritical water-cooled reactor. Okay, that's all my talk. Thanks for your attention.
Thank you, Professor Zhang. If you have questions, go ahead and type them in the question pane now. And while questions are coming in, we'll take a quick look at the upcoming webinars that we have scheduled. In September, a presentation on the EPRI virtual reality training. October, the nuclear workforce of the future, opportunities and needs for international nuclear sector. And in November, MOOC, the knowledge management method applied to a Gen 4 project, the continuation of a successful story. The first question is, I think you have mentioned that cold work increased general corrosion resistance. If so, can you explain why the cold work or higher dislocation density can increase general corrosion resistance?
Yes, that's how should I say? Let's moving the slides is very difficult now.
Oh, we can do that.
Work. So the code work in physics is related to the diffusion, the dislocation in the material, in the matrix of material. So deformation is the mechanism of the deformation is in the metallic materials is the dislocation movement of dislocation, and when we have higher density for dislocation, then the chrome Cr element diffusion will have a much higher diffusion rate. So at how can I move the slides upwards? So wait a minute, please. So when we let's say I have the slides with the diffusion rate of chromium.
If you know the slide number, I could type it in, but otherwise this is about the best we have. Okay, here we go.
Yeah, here we go. So here the diffusion rate of chromium in the material is look here. This is a total diffusion rate of chrome, and here this part is a dislocation density contribution, and here this is the other part contributed by green boundary. So if we can't have high density of this green boundary, we need dislocation density to assist the diffusion of chrome. And this is very important to supply chromium to the surface oxide, because it is majorly this oxide, chromium, Cr2O3, is a major form of protective oxide on the top of a stainless steel or nickel-based alloy. So, however, this chromium will react with oxygen and water to form as gases here, or chromate and dissolve into the water or evaporate to the steam. So we need to supply constantly the chrome to maintain the protectiveness or the integrity or the integrity, the protectiveness of this scale, so that this scale is very intact and can prevent the diffusion of iron from matrix material outward to the surface of the material, and it can also stop the diffusion of oxygen from water to the material matrix. So this is very important. And why we add aluminum and silicon is that they can form a composite surface oxide along with chromium and the aluminum and silicon, so that this protective oxide will be much intact and have better protectiveness, and so to reduce the general corrosion rate. This is very important. And if we check our data, in especially alloy 800H. We've done on alloy 800H. Here. This we can say, oh, I'm sorry. So here, this figure. For this figure, we use the cold rolled materials from with deformation from 20% up to 80%. This is cold rolled, and we polish the coupons so that the coupons can show exactly the general corrosion rate of those cold rolled material with well-defined dislocation density in the material. So these are the data. With the increase of the cold deformation, the dislocation density increases, and the general corrosion rate decreases. And here we use grinding. Grinding will leave a surface with very heavily deformed surface, And this heavily deformed surface, very thin surface, maybe about 2 to 10 micron. And this heavily deformed surface layer in supercritical water at 600 degrees centigrade will recrystallize to nano size grains and still keeps high density of dislocation. So if we have this fine layer, then we have further lower general corrosion rate as compared with this. This is cold rolled with polished, and it is this figure, this curve here, this curve. So we have further these two figures shows exactly the importance of dislocation density in the material, in the general corrosion rate of the material. This is very important. Okay, I don't know if this answers your question well.
Oh, I sure hope so. That was fantastic response. Thank you. The next question is, what crack growth rate would be considered good for a fuel cladding material?
I beg your pardon, which crack growth rate?
Would be considered good for a fuel cladding material?
For fuel cladding material, we want no cracking, because even no crack initiation in the material, because the fuel cladding is too thin. It's just
Did I lose you?
Stainless steel or nickel-based alloy 800H. We consider the fuel cladding thickness is only 0.4, so 400 micron. If you have initiation of a crack, then we'll soon make it break. So that's very dangerous. Although we show here, I think, I'm sorry. Oh, no move in the slides. Are
you going forward?
Yes, forward and forward. Here. Sorry, I moved too fast and rebounds. Okay. Here we say that look, at temperatures below 500 degrees centigrade, we say that if we apply a K of 25 megapascal, this is actually a very high crack K for material in this temperature environment and material. So here we can see that the corrosion rate is not slow, it's very high. It's about 5 or 6 times 10 to the minus 6 millimeter per second. This is very high. So if we consider not to introduce cracking, we need to reduce K. So we have to make the surface of the fuel cladding to be very smooth, no defects. And if we have good general corrosion resistance, then we would avoid the crack initiation, so that to avoid the crack growth. So that's our expectation. So we expect no crack initiation, no crack growth.
Thank you.
So we need further to study to reduce the K, so that we can obtain a K when the crack stops, or crack initiation stops. So that's our aim, but presently we still don't have time to do that.
Thank you.
Okay, thank
The
you.
next question is, from the SCC point of view, which steel alloy is the best to resist corrosion and have the long service life for SCWR?
So I think it should be this alloy 800H, because it has a better, it has a little better strength in compare with alloy 310S, because currently we select alloy 800H and 310S, these two materials as the best candidate. And in my point of view, alloy 800H will be a little better because 310S will be worse than this material in the aspect of crack growth rate, because it has 310S has lower strength and no strengthening method. And in this case, it has much higher crack growth rate in compare with alloy 800H.
Thank you.
Thank you.
The next question is, thanks for your great presentation. My question is, does that help to decrease the corrosion rate by coating CR layer just like the ATF concept?
That's a very good question. We've ever seen this application in Chinese university, Xi'an Jiaotong University. They've done this in several years ago, and we see that in deaerated supercritical water, if we inject a little bit a low concentration of hydrogen, so that the water is reducive. In this case, chromium will be stable. And coating with chrome coating is a good way to have good resistance to general corrosion. But if we add this material, add oxygen, or if we can't control oxygen in the fluid, then we have the chrome gone very quickly, because oxygen will turn the chrome into chromate, and 6 valence chromate. So this will be vaporized and dissolve into water and evaporate away bring away by the water very quickly. So if we want to use chrome CR coating, we need to control the water chemistry of the reactor, so that to maintain the chrome coating for a little bit longer time. So that's my answer. Thank you.
Thank you.
Uh-huh.
That's the list of questions. Oh, there's one more. There's a bunch of accolades coming in, so I'm going to go ahead and post those because I agree. Today was a fantastic presentation, so thank you very much for all of your efforts. The next question is what about silicon carbide?
Wow, silicon carbide. We didn't see much silicon carbide in the material, although we alloy the material in. I'm sorry, I may made some mistake. In silicon, you mean silicon carbide matrix or composite fuel cladding material? Is that so? Or if we consider silicon carbide as a fuel cladding, this pure silicon carbide is very soluble in supercritical water. So in our lab, we've done a lot of exposure tests in especially in the liquid water. Silicon carbide dissolves very quickly if without a coating for corrosion-resistant coating. So I don't think silicon carbide is a good way to be used as fuel cladding in water-cooled reactors. It is not good. But for supercritical carbon dioxide, this kind of gas-cooled reactor, maybe it will be a good choice. But for water-cooled reactor, no. It will gone with water. Okay.
Thank you.
So I don't know if you are satisfied with my answer.
Thank you. It seems that 800H, which contains high nickel, is better. Then why should you consider Haynes 230, which has the quote best creep resistance and quote best oxidation rate?
I think the major alloy element to resist to have lower general corrosion rate is chrome. So usually we have lower general corrosion rate in 310S in compare with alloy 800H. These two materials for the nickel concentration, they usually maintain higher creep rate of the material, but in general corrosion rate, the nickel concentration is not that important, but chrome concentration is very important in general corrosion. So if you want a good general corrosion resistance, 310S will be a little better. But if for how should I say the cracking, if we balance the cracking and the general corrosion cracking, perhaps a alloy 800H will be a little bit better in my point of view. But at least these two materials, if we compare with those materials we developed at present, so the AFA material alloys, it usually has much better performance than these two, and in the aspects of general corrosion and stress corrosion cracking, at least they are comparable. How should I say? So we need much work in the future to evaluate these materials. So a big amount of work facing us. So very difficult for future.
Thank you.
Okay, thank you.
Thank you very much for sharing your expertise and your passion for teaching with us today. I can't get over your enthusiasm for the topic and your presentation style. I've just thoroughly enjoyed it. And I think you can tell from the number of questions and the type of questions that the audience did too. So thank you very much.
Okay.
Thank you. Thank you.
Thank you. Thank you all.
Patricia, do you have any closing thoughts before we end today?
Thank you very much, Professor Zhang. Your passion and your dedication and all the answers that you gave, I see that. I'm sure you're enjoying this field, and the people who have the chance to follow your classes are very lucky. So again, thank you very much for your contribution to the Gen 4 International Forum. Thank you, Professor Zhang.
Okay, thank you.
Thank you. With that, we're going to go ahead and close for today. Bye-bye.
Bye-bye.
Bye-bye. It's my great pleasure. Thank you.